Okay, folks, I put together this code here called FFT results in Instrumentation Spring 2020 to basically talk about what happens when you run through a frequency sweep and you want to plot the magnitude of a waveform. So I have this function here called waveform, and it takes in a time vector. And right now, the magnitude of this sine wave is 1, and it's got this coefficient in front of it, 2 pi 10 times t. Now, if you look at sine of 2 pi 10, this 10 here is actually f in frequency. And the reason why I know that is because 2 pi times f times t, and sorry, let me see if I can make this bigger. 2 pi times f times t, that needs to be in radians because when you do a sine function, the input argument has to be in radians. So if you look at all these things, right, 2 pi is in radians, f is in 1 over seconds, which is hertz or frequency, and then t is in seconds, right? And so basically f times t, that cancels out and you just get radians. Another way you can look at this is that w is 2 pi times f, and that's in units of radians per second, right? Because you have 2 pi, which is radians, and then f is per second. And so when I make some plots further down in the code, let's remember that what we're looking at is frequency of this wave. So the frequency of this wave is 10 hertz, or in this case, it would be 20 pi radians per second, right? So I could just, if I wrote this out, I could just say like, this could just be 20 pi. And remember, you've got to do 20 pi divided by 2 pi, which would give you 10 hertz. Okay, so that's how you get the frequency of the waveform there. So what I'm going to do is I'm going to create this vector from 0 to 1 seconds, and I'm going to use like a ton of data points here just to make sure that I plot it correctly. And then I'm going to do f equals waveform of t. So I've grabbed the waveform up here. And then I'm going to, the frequency of my waveform is 10 hertz. And in order to make sure that my FFT works properly, I need to make sure that my sampling frequency is 2 times the frequency. So I could just do 20, but I'm just going to sample I'm just going to sample the waveform at 100 hertz just to make sure that I don't run into any aliasing issues. And so I make this time vector here, and then I make the waveform, and then I go ahead and plot it. Okay, and so you're going to see here, I basically have, oh, did I not show it at the bottom? Let me show it. So here is my 10 hertz waveform, right? So basically every 1 second I have 10 humps. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I've got 10 cycles per second. That's what 10 hertz is, right? The FFT that I'm doing, I'm computing the coefficients of the sine wave. And if you remember in the last video that I posted, in order to compute the coefficients of your input signal, you have to do an integral of your input signal. And so this here is basically a crude Riemann sum. It's not really important for you to understand, but it's a crude Riemann sum where I integrate to compute the coefficients. So what I'm doing though is I have this coefficient n in here, and n is multiplied by omega naught, where omega naught is just 2 pi. This f naught is irrelevant. I don't actually need it in there. And so when I say n equals 0, or let's say n equals 1, what I'm saying is compute the magnitude of that sine wave, or sorry, compute the magnitude of my input signal at a frequency of 1 hertz. And when I do this code, what I find is that the magnitude of my signal at 1 hertz is practically 0. That's 10 to the minus 16. If I do 9, I still get 0, essentially 0. But if I do 10 here and I run this code, I get 0.999. And why did I get 0.999? Well, that's because the magnitude of this waveform is 1. So I could put 1.3 in here and run the code again, and now what I'll see is that at 10 hertz, the magnitude is 1.3. So what I can do here then is I can actually add another frequency. So I can say, okay, you know what? Why don't I make my waveform 2 frequencies? So I've got a frequency of 10 hertz with a magnitude of 1.3. a frequency of 15 hertz, and a magnitude of 0.8. And I can run the code again. Now my waveform looks totally different, right? Because I've got two frequencies. I've got one at 10 hertz, and I've got one at 15 hertz. But the FFT program that I wrote doesn't care. At 10 hertz, you've got a magnitude of 1.3. So what do you think is going to happen if I do a frequency of 15? Well, I should get 0.8, right? At a frequency of 15, I've got a magnitude of 0.8. So if I run this, I got 0.8. So that means it's working pretty well, right? So let's grab a third frequency. So let me do negative 1.2 and a frequency of 4. So now let's go through my different frequencies. So at 15, I should have 0.8. At a frequency of 10, I should have 1.3. And at a frequency of 4 now, I should have negative 1.2. And so what this frequency sweep is doing is it's computing the magnitude of all the three different frequencies. Now here's the thing. You could easily generate a plot where you go from, say, 0 to 20 hertz and plot the magnitude of the frequencies of every wave. To do that, all you would do is just loop through, and so I could just make a loop here where I loop through n from 1 to 20. I'm going to comment out this line of code, and now I'm going to hit F5 here, and so now I'm going to get a bunch of different values here, and so now at a frequency of 1, 2, and 3, I've got almost 0. At 4, I've got minus 1.2, right? That was my first frequency. Then I've got a bunch of zeros, and then at 10, I have 1.3, and then a bunch of zeros, and then at 15, I have 0.8. So I could even plot this, so I could go down here and say, you know what, get rid of this print, I don't really need this anymore, and then plot this and put frequency on the x-axis, magnitude on the y-axis, and then I'm going to plot the absolute value of the coefficient because that's typically how FFTs work. And I forgot to grab my figure. And so now here's my waveform. And I guess I didn't plot it. Oh, I didn't plot it. And there you go. So this waveform here in the right part of your screen has three fundamental frequencies in it. It's got a frequency of 4 with a magnitude of 1.2, a frequency of 10 with a magnitude of 1.3, and a frequency of 15 with a magnitude of 0.8. Now, if you think about this graph here on the left, I could easily do this graph by hand. You could use this fancy code and generate these two plots, but if you think about it, it's pretty straightforward to generate this plot. And how do you do it? Well, you don't actually need to plot this first figure. All you need to do is go here and say, okay, what is the frequency in hertz of this sine wave? Well, it's 20 pi over 2 pi, which is 10. So at 10, you just plot the magnitude of 1.3 and you draw a line. Boom, 1.3. At 15 hertz, you just draw a line to 0.8. And then at 4 hertz, you draw a line to 1.2. And so you can easily generate this plot by hand with not too much effort. The reason why a lot of people like to run these codes is to show you what happens when you run into aliasing issues. So look at this, for example. I've got a frequency of 4, 15, and 10. Since I have a frequency of 15, my Nyquist frequency is 30. So if I sample at 31 hertz, my FFT plot should still look the same. And it looks like I actually bled over. I see I ran into some leakage here. Okay, I already ran into leakage. Let's do like 35 and see if we can get rid of that leakage. And there we go. Okay, the leakage is gone. Now let's go down to 25, right? So now I'm definitely going to run into aliasing issues. And let's see what happens. Look at this. All of the magnitudes are wrong. So at 10 hertz, I'm getting a magnitude of 0.5 because I'm not sampling correctly. If I go even lower. My lowest frequency was 4 hertz. Let's see what happens if I sample at 2 hertz, right? Yeah, I didn't even grab anything. This is 1E29, so I didn't even grab it correctly. So let's try 4 hertz now. Let's see if we can at least grab that first fundamental frequency. And I'm just completely, screwing this up here because I'm not sampling fast enough. Let's try 8 hertz. That's 2 times the first frequency. Let's see if we can at least get the frequency at 4 hertz. And so I didn't grab it. Here's 4 hertz, and I'm not grabbing it. I'm still running into aliasing issues. And so until I get up to, 35, where I'm, so it's not 35. Yeah, it's 35. Until I get to 35, I'm going to run into aliasing and leaking issues. And so you can generate this plot by hand, but unless you could use a computer, you're not going to learn about aliasing and leakage. But at least if you do this plot by hand, you can at least get, some experience in magnitude versus frequency plots and looking at that. And this is what I did when I was recording my voice, right? So I recorded my voice and I had the code run a frequency sweep through my voice and plot the highest frequency. So that's why when I made that sound with my voice, I got a frequency of 420 hertz because that was the sound wave that was coming out. That was the fundamental frequency that was coming out. Okay, I hope this helped learning about aliasing and frequency sweeps and FFTs. If you have any questions, post in the comments, and I hope you have a nice day.